In this chapter, we will start studying probability distributions. In chapter 6, we will cover discrete probability distributions, and then in the next chapter, we will study continuous probability distributions. The learning objectives for this chapter: one is to identify the characteristics of a probability distribution, and we will define what a probability distribution is. Then distinguish between discrete and continuous random variables. If you recall, when we discussed different types of data, chapter 1, we said that there was discrete data and there was continuous data. We will also see that there's a distinction between discrete random variables and continuous random variables. Next learning objective, number 3, we will do some calculations. We want to see how to compute the mean, variance, and standard of deviation of a discrete probability distribution. Number 4, we will begin studying some important discrete distributions, and the first one will be the binomial distribution. Explain the assumptions of the binomial distributions and apply it to calculate probabilities. Next, we will explain the assumption of the hypergeometric distribution and apply it to calculate probabilities. The hypergeometric distribution is another example of discrete distributions, and we will take a look at that. The definition of a probability distribution: it's a listing of all the outcomes of an experiment and the probability associated with each outcome. We have a probability experiment, and all the outcomes are known. A probability distribution in this case is a listing or a table that lists all the possible outcomes and the probability for each of these outcomes. Some of the characteristics of a probability distribution follow from what we learned about probability. One, the probability of a particular outcome is between 0 and 1 inclusive. 2, the outcomes are mutually exclusive. Mutually exclusive, as we learned last chapter, means when you have an experiment, only one of the outcomes will occur. Once one outcome occurs, that means none of the other outcomes has occurred. Number 3, the list of outcomes is exhaustive. That meant that when you conduct the experiment, one of the outcomes will occur. The listing of all outcomes is exhaustive. It covers all the possibilities. And as a result, the sum of all probabilities of the outcomes is always equal to 1. Here is an example. Drug manufacturers may claim a treatment will cause weight loss of 80% of the population. This claim can be tested by a consumer protection agency using a sample and statistical inference. You certainly can take a sample and collect the data, checking how many people in that sample actually lost weight, using this treatment. So you can use probability, you can use the data from the sample and statistical inference to verify the claim. Here is an example of a probability distribution, and it will be a discrete probability distribution. Suppose we are interested in the number of heads shown face up with 3 tosses of the coin. The possible outcomes is either you get 0 heads, or 1 head, 2 heads, or 3 heads. How many possible outcomes when you toss 3 coins? Each time you toss the coin, there's 2 possible outcomes, heads or tails. For the number of outcomes when you toss the coin 3 times is 2 times 2 times 2, which is 8. That follows from the rule of counting we learned the product rule. We learned that rule in the last chapter. For the 8 possible outcomes are listed in the table, and each طبعا outcome will list the results of the first, second, and third toss, and in the last column we count the number of heads that we get from the possible result. For example, the first possible result is getting tail in each toss, which means you have 0 heads. In the second possible result, you get tail, tail, head. The number of heads is equal to 1. For every possible result is listed and the number of heads is counted. You will notice that there is only one result that will give you 0 heads. There's 3 different results that will give you 1 head, and 3 different results that will give you 2 heads, and 1 result that will give you 3 heads. Thus every possible number of heads is listed, and every possible result of the experiment is listed and the number of heads counted. Now since we are interested in the number of heads, we will call this a random variable. This random variable, which we will call x, can take the values 0, 1, 2, or 3. Either 0 heads, 1 head, 2 heads, or 3 heads. Now a probability distribution for this variable will be a listing of all the possible outcomes for x and the probability of that outcome. So here is this table. This is our distribution. The number of heads, which we called x, can be 0, 1, 2, or 3. Now what is the probability that x equals 0, meaning we get no heads? There's only one outcome that gives me no heads, but the probability is 1 over 8, which is 0.125. The probability that x equals 1, meaning we get 1 head, there's 3 outcomes that give me 3 heads. There's 3 outcomes that give me 1 head, but the probability of x equal 1 is 3 divided by 8, or 0.375. Same for x equal 2. I have 3 outcomes that results in 2 heads, but the probability of x equal 2 is 3 over 8, or 0.375. Finally, there is the probability of x equal 3, meaning we get 3 heads. There is only one outcome, and therefore the probability is 1 over 8, which is equal to 0.125. For every possible value for x is listed, and the probability for that value is written. For that gives you now a probability distribution for the number of heads. طبعا the probability, the sum of the probabilities must equal to 1. To the right you have a graph. طبعا a distribution can be graphed. In this case the horizontal axis lists all the possible values for x, the number of heads, 0, 1, 2, 3. The height gives you the frequency, which is the probability of each of these values. Here is now a definition for a random variable. Actually, the example we just looked at, the number of heads, is a random variable. Here is now a definition for a random variable. In any experiment of chance, the outcomes occur randomly and so are called random variables. A random variable is a quantity resulting from an experiment that by chance can assume different values. طبعا we just saw an example. The number of heads you get when you toss 3 coins is an example of a random variable, and the possible values that variable can take are 0, 1, 2, or 3. Here are more examples. The number of employees absent from the day shift on Monday. طبعا that number can be 0, no absence, 1, 2, 3, up to the number of employees available. But this is an example. The number of employees absent is an example of a random variable. The grade level, طبعا grade level is either freshman, sophomore, junior, or senior of the members of the St. James High School varsity girls basketball team. طبعا the grade level is also a random variable. One type of random variable is discrete random variable. طبعا discrete random variables are usually the result of counting. If you recall, when we discussed the different types of data, one of the types we discussed was discrete type of data. فإذا you can think of a discrete random variable is a random variable that takes on discrete values, and that normally happens if the random variable is anytime there is counting, the result will give you discrete data. In the case of random variables, you will have a discrete random variable. Here's the definition. Discrete random variable is a random variable that can assume only certain clearly separated values. The first example we looked at was the coin, tossing a coin 3 times and counting the number of heads. Certainly the values that we looked at were 0, 1, 2, 3. These are discrete values, and therefore this is an example. The random variable that counts the number of heads is a discrete random variable. A bank counting the number of credit cards carried by a group of customers. طبعا the number of credit cards can be 0, 1, 2 up to a number of credit cards. But again, this is an example of a discrete random variable. Here is the example of the credit cards. For the Bank of the Carolinas, they count the number of credit cards carried by a group of customers. The number of cards carried is a discrete random variable, as we just stated. Here's now a distribution that gives the different possible values for the random variable and the probability, the different possible outcomes and the probability for each outcome. And that طبعا will give us a distribution for the discrete random variable. Here is the first column is the number of credit cards. They can be 0 or 1 or 2 or 3 or 4 or more. The probability that x is equal to 0 is 0.03. Probability x equal 1 is 0.10. Probability of x equal 2 is 0.18. Probability of x equal 3 is 0.21. The probability that the number of credit card is 4 or more is equal to 0.48. طبعا the sum of the probabilities must equal to 1. Here's another example of a discrete random variable, and طبعا this table represents the distribution for this random variable. طبعا the other type which we will study in more details in the next chapter are continuous random variables. And continuous random variables can assume an infinite number of values within a given range. Continuous random variables are the results of measuring. So this we should remember when we discuss different types of data, continuous data was the result of normally anytime you're measuring, the result will be continuous data. A continuous random variable will be now a random variable that assumes continuous data. And here are examples. The time between flights between Atlanta and LA are 4.67 hours, 5.13 hours, and so on. Anytime your measurements here represent time, this is an example of a continuous data, and therefore a random variable that measures the time between flights can be thought of as a continuous random variable. The annual snowfall in Minneapolis, Minnesota, measured in inches, طبعا also is considered to be a continuous random variables. Anytime there is measurements involved, the result will give you a continuous random variable. Now we are ready to do some calculations. We want to see how to calculate the mean and variance of a probability distribution. Now, a probability distribution is the result of a random variable. You can we will define and calculate the mean for the distribution and also the variance. The mean is a typical value used to represent the central location of the data, as we did when we worked with data before. The mean is also referred to as the expected value. When you are working with random variables, the mean is also we call it sometimes the expected value. So here is the definition of the mean of a probability distribution. This is, of course, in the discrete case. Mu, which is the mean for the distribution, is equal to the sum of x times p of x. The sum runs over all the possible values of the random variable. If I take every value, x, multiplied by the probability for that value, add all those sums, those products, the result is mu. The result will be the mean of the probability distribution. But in the discrete case, that should not be too hard. Then your distribution is just a listing of the different values for x and the probability for each x. So you can calculate the mean by multiplying each value by the probability for that value and adding all these products. The other thing we will calculate is the variation. The amount of spread or variation in the data is described by the variance. For the variance for a probability distribution, which we will call sigma squared, is the sum of x minus mu squared times p of x. And again, the sum runs over all possible values for x. For every value for x, subtract the mean, square that quantity, and multiply by the probability for x. You do this for every possible value for x, and add the sum of all these products. The result will give you the variance, or sigma squared. The standard of deviation of the probability distribution is the positive square root of the variance. But you need to calculate the variance and then take the positive square root of the variance. That will give you the standard of deviation for the probability distribution. Here is an example of calculating the mean for a probability distribution. John Ragsdale sells new cars for Pelican Ford. Well, John is a car dealer. He sells cars. He usually sells most cars on a Saturday. He has developed a probability distribution for the number of cars he expects to sell on Saturday. For the table to the left is a probability distribution for the number of cars he expects to sell. The values for x, the number of cars, is 0, 1, 2, 3, or 4. But for each value here, the probability is listed in the second column. For example, the probability that x equals 0, meaning he would sell no cars, is 0.1. The probability for 1 is 0.2. Probability for 2 is 0.3. The probability he would sell 3 cars is 0.3. Finally, the probability that he would sell 4 cars is 0.1. And this is a probability distribution, but the sum of all the probabilities has to be equal to 1. For what type of distribution is this? This is a discrete distribution, and the variable x takes on discrete or separate values. How many cars does John expect to sell on a typical Saturday? We're looking for the mean. The expected value is the same thing as the mean. That's what we will do, is we will calculate the mean for that distribution. And number 3, we would like to calculate the variance, but you need to start with the mean, and because you need the mean to calculate the variance. The table to the right, now we will do the calculations for the mean. The first 2 columns is the probability distribution we started with. For the first step is to add a third column. For each value of x, multiply x by the probability of x. For example, 0 times 0.1 is 0, 1 times 0.2 is 0.2, 2 times 0.3 is 0.6, 3 times 0.3 is 0.9, 4 times 0.1 is 0.4. This is just for each row, multiply the value for x times the probability of x. We need to take the sum of values in this column. That will give us the mean. For the mean in this case, mu will be 2.1. Next, we will use the value for the mean because we need to also calculate the variance. But now that we have the mean, we can go ahead and calculate the variance. The computational steps which we will do in the table, that first of all you subtract the mean from each value of x, then square that quantity, then multiply the square of the quantity by the probability for x, and then add the sum of all those products. That will give you the variance. So again, the first 2 columns are your probability distribution. For each row, start by subtracting x minus mu, from each value for x subtract the mean, which we already know to be 2.1. You do this to every value of x. In the next column, you have to square that quantity for each x. Evaluate x minus mu squared. And then you do this again for every x. In the final column, take x minus mu squared and multiply it by the probability of x for each x. This last column, if you add all those products, the sum will give you the variance. In this case, the variance, sigma squared, is equal to 1.290. If we need to know the standard of deviation, then we need to take the square root, or the positive square root, of 1.290. Now we're ready to consider some important discrete distributions. They are important because many situations, many data would follow the binomial distribution. Also with the binomial distribution, you can calculate the mean and variance, we have formulas to calculate the mean and variance. But to have a binomial distribution, there are 4 requirements that must be satisfied to have a binomial probability distribution. The first one is that there are only 2 possible outcomes, and the outcomes are mutually exclusive as either success or failure. The best example for that is tossing the coin. Tossing the coin has only 2 outcomes, either heads or tail. You may consider heads to be a success. For each outcome here of tossing the coin will be either a success or failure. We already know what mutually exclusive means, that only one of the outcomes will occur. Either you get a success or you get a failure. The number of trials is fixed and known. For example, you may toss the coin 10 times. If in each time you toss the coin, there's only either you'll get a success or you'll get a failure. The probability of success is the same for each trial. For that same example, every time you toss the coin, the probability of getting a head, which is success, stays the same, which is 0.5. Each trial is independent of any other trial, meaning the result that you get from any given trial has nothing to do or is not affected by any other outcome, يعني the outcome of any other trial. طبعا we gave an example already of a binomial distribution. For example, if I toss the coin 10 times and consider to be getting ahead to be success, here the probability of success is 0.5, n, which is the number of trials, is 10, and that طبعا satisfy all these conditions. Each outcome is either a success or failure. The number of trials is fixed and known. In our case, is 10. The probability of the success is the same, which is 0.5 in this case. And finally, each trial is independent of any other trial. Here is another example. A young family has 2 children, both boys. The probability of the third birth being a boy is still 0.50. The gender of the third child is independent of the gender of the other 2. طبعا this is an example that one of the things that we need to be able to do is to recognize the experiment as a binomial experiment that will give me a binomial distribution. Now with families, anytime there's a birth, there's 2 outcomes. Either you get a boy, طبعا assuming you only get 1 child. Either you get a boy or you get a girl. For example, if you consider success to be getting a boy, then the probability of success is 0.50. We assume that the probability of a boy is the same as the probability of a girl, so each one of these probabilities is equal to 0.50. Now, since this family has 2 boys, that means the outcomes of the first 2 trials is a boy, which you can think of as success. Now what happens on the third trial? The probability of a boy is still the same. It is 0.50. The gender of the third child has nothing to do with the gender of the first 2. That type of experiment is considered to be a binomial distribution. Here is the official definition. Of course, the number of trials is n, that is known and fixed. N is the number of trials. The probability of success, we use pi. The symbol pi is used to refer to the probability of success. For any binomial probability, you need those 2 numbers. You need to know the number of trials, n, and you need to know the probability of success, which is equal to pi. Here are the conditions listed now as a definition for the binomial probability experiment. An outcome on each trial of an experiment is classified into one of 2 mutually exclusive categories, either success or failure. The random variable is the number of successes in a fixed number of trials. طبعا you are doing the experiment n times, you count the number of successes. طبعا the number of successes could be 0, 1, 2, up to n, the number of trials. The probability of success is the same for each trial, and the trials are independent, meaning the outcome of one trial does not affect the outcome of any other trial. There is here an important note. طبعا we use pi to refer to the probability of success, but that changes from one experiment to another. The warning here is do not confuse the symbol pi with the mathematical constant 3.1416. Pi here does not refer to that number, it just refers to the probability of success. As we will see, طبعا when you are using the binomial probability experiment, you need those 2 things. You need to know n, the number of trials, and you need to know pi, which is the probability of success. And طبعا when you are working with a problem that deals with the binomial, you need to recognize from the description of the experiment, you need to recognize it as a binomial probability experiment. You need to also recognize what n is and what the value for pi is. And we will do some examples. The nice thing about discrete distribution like the binomial, and you have formulas to calculate probabilities. For the binomial probability distribution, with n is the number of trials and pi the probability of success, p of x, the probability for any value for x, the number of successes, is equal to n choose x. N is the number of trials, x is the value we're calculating the probability for, times pi raised to the power x, times 1 minus pi raised to the power n minus x. Now sometimes we refer to, since pi is the probability of success, we refer to 1 minus pi as the probability of failure, because it's a complement. So let's read the formula again. P of x, the probability of x, is equal to n choose x, pi raised to the power x, times 1 minus pi raised to the power n minus x. Okay, here is an example. طبعا this formula you can calculate the probability for each value of the random variable, which counts the number of successes. So you can calculate the probability for any number of successes. طبعا to have a distribution, you need to calculate the probability for each possible value for x, the number of successes. Here is an example. There are 5 flights daily from Pittsburgh using US Airways into the Bradford Regional Airport. That's a city in Pennsylvania. There's 5 flights. Suppose the probability that any flight arrives late is 0.20. For here, you have 5 flights. For n is equal to 5. Now each flight is either late or it is not late. But here, since we are given the probability that the flight arrives late, this is considered to be our success. Flight arriving late is success, and the probability of success is equal to 0.20. So now that I know the 2 things I need is n, the number of trials is 5, the probability of success is 0.20. Here success is that the flight will arrive late. Let's calculate some probabilities. For example, what is the probability that none of the flights are late today? طبعا none of the flights late, that means x is equal to 0. Here is the formula listed again. Let's read the formula again. The probability of x is n choose r, pi raised to the power r. Here this really should be x. Now we're taking the probability of x, so this should be n choose x, pi raised to the power x, 1 minus pi raised to the power n minus x. For the probability of 0, take 5 choose 0 times 0.20 raised to the power 0 times 1 minus 0.20 raised to the power 5 minus 0. Here x is 0 and n is equal to 5. 5 choose 0 is 1. 0.20 raised to the power 0 is also 1. This number here, you need a calculator for some of those calculations. This is 0.8 raised to the power 5, which is 0.3277. The product will give you 0.3277. Then the probability of no flight arriving late is 0.3277. Let's calculate another probability. What is the probability that exactly one of the flights is late today? That means we want the probability that x is equal to 1. This is the probability of 1. This is 5 choose 1 times 0.20 raised to the power 1 times 1 minus 0.20 raised to the power 5 minus 1. These numbers are not quite accurate, and a 5 choose 1 should be 5. 0.20 raised to the power 1 is 0.20. The product is 1. The product is correct. But just to be accurate, 5 choose 1 really should be 5. and 0.20 is raised to the power 1 is 0.20, the product will give you 1. Times, this is 0.8 raised to the power 4. You need your calculator for that. You will get 0.4096. The product is 0.4096. This is the probability that exactly one flight will arrive late today. طبعا, if you want to write the distribution, you need to do the calculations for every possible value for x. طبعا, the possible values for x is 0, 1, 2, 3, 4, and 5. The maximum will be the number of flights. This is done for us in the next slide. Here is now the distribution for that problem with the remaining probabilities calculated. But this is the same problem. You have 5 flights, and the probability of a flight arriving late is 0.20. The possible values for x is 0, 1, 2, 3, 4, 5. طبعا, the first 2 columns is your probability distribution. For each possible value for x, the second column includes the probability that x is equal to that number. طبعا, now we already calculated the probability for x equals 0 and the probability of x equal 1. The remaining probabilities are calculated in the table. The first step is to calculate the mean. The mean, you need to add a third column for x times p of x. And for each value of x, multiply it by the probability for that x and record it in this column, x times p of x. The sum of all those products will give you the value for the mean. In this case, the mean will be 1. Now that you have the mean, you could continue to calculate the variance. Your next column is x minus mu. And for each value for x, subtract the mean, which is 1, and here is the column that calculates x minus mu for each x. Next, you want to square each quantity, and square each value for x minus mu. This is the column x minus mu squared. طبعا, all of these values should be positive or 0. In the final column, multiply x minus mu squared times the probability of x, and you do this for every row, for each value for x. The sum of all those products will give you sigma squared, or the variance. The variance here will be 0.797. Next, we would like to see shortcut formulas. طبعا, we already calculated the mean and variance using the table, but there are shortcut formulas where you can calculate the mean and variance of the binomial distribution. The mean for the binomial distribution, mu is equal to n times pi. Take the number of trials times the probability of success will give you the mean. The variance, sigma squared, is equal to n times pi times 1 minus pi. For our preceding example, n was 5, and now we had 5 flights. Pi, the probability of success, is 0.20. So the mean, using the shortcut formula, the mean mu is equal to n times pi, which is equal to 5 times 0.20, which is equal to 1. And that's exactly the same value we got from the table. The variance, sigma squared, is equal to n times pi times 1 minus pi, which is equal to 5 times 0.20 times 1 minus 0.20, and that should give you 0.80. Now, in the table, we have the value for the variance was 0.7996. طبعا, there is a slight difference because in the table, when we did the calculations, all these products were rounded. When you add all those rounded results, the final result might be slightly different than the variance you will get applying this shortcut formula. But it is very close, and if you round the result from the table to 2 decimal places, you will get 0.80. Now, because the binomial probability table is used a lot, but there are tables that are already constructed for use with the binomial distribution. طبعا you have different tables for different values of n. For example, this picture here, or the table we have here, is for n equals 6. And now for the probability of success, you have several columns for different probabilities. The first column here is the values for x, the number of successes, 0, 1, up to 6. Now with n equals 6, the number of successes could be 0, 1, 2, up to 6. If the probability of success is 0.05, which is the the highlighted column, then here is the probability are listed for us. The probability of x, or the number of successes equal to each value in the first column, is listed in that column. طبعا if the probability of success is different, there are the other columns cover the other probabilities of success. There are tables for different values for n, and طبعا for each value for n there is several probabilities that represent the probability of success. You can actually, if you have a situation where you have a table that's already calculated for you, you can use it to calculate probabilities. Next, we would like to look at the cumulative binomial probability distributions. When we discussed different graphs in Chapter 2, we looked at cumulative distributions, and cumulative means you are adding probabilities. طبعا we will look at an example which will be a binomial distribution, and see how we can calculate cumulative distributions. This example, a study by the Illinois Department of Transportation concluded that 76.2% of front seat occupants wore seat belts. طبعا that means both occupants in the front seat were using their seat belt. طبعا what that percentage means, 76.2, this is actually a probability. If you select a car at random, the probability that both occupants, front seat occupants, are wearing seat belts is 0.762. Now we want to compare the information with the current usage. We want to test this result. We can take, in this case, we will take a sample of 12 vehicles, and we want to calculate different probabilities. And again, before you do any calculations, you must recognize this as a binomial experiment. You are looking now for cars where people are wearing seat belts. For any car you pick, the front seat occupants are either wearing seat belts or not wearing seat belts. Here we're given the probability that the front seat occupants are wearing seat belts, but that's your success. Success is that when you stop a car, that front seat passengers are wearing seat belts. Probability of success is 0.762. Now our sample has 12 cars, for n is equal to 12. In this binomial experiment, n is equal to 12. The probability of success is 0.762. If we want to calculate probabilities using the formula, for 1, we want to calculate the probability that the front seat occupants in exactly 7 of the 12 vehicles are wearing seat belts. And the probability of 7 successes, the probability is x equals 7. Now there's exactly 7 of the 12 vehicles are wearing seat belts. For here, again, the formula is listed. We want the probability that x equals 7, or p of 7. This is n choose x, so it's 12 choose 7, times the probability of success, which is 0.762 raised to the power x, which is 7, times 1 minus 0.762 raised to the power n minus x, which is 12 minus 7. طبعا again, this is definitely something you need a calculator for. 12 choose 7 is 792. This number 0.762 raised to the power 7 is equal to 0.149171. The third number, this would be raised to the power 5, and the result should be 0.000764. The product of all those numbers is 0.0902. طبعا you can do all those calculations in one step, or you can do it like it's done in this example. You calculate each number separate and multiply them. The result is 0.0902. Now that gives you the probability, and exactly 7 out of the 12 cars the occupants are wearing seat belts. This is not cumulative. This is just calculating the probability for one value for x, which is in this case it's 7. The second problem will give you a cumulative probability. What is the probability that at least 7 of the 12 front seat occupants are wearing seat belts? When you say at least 7, that means 7 or more. So you want the probability that either 7 people are wearing seat belts, or 8, or 9, or 10, or 11, or 12. That's what at least 7 means. 7 or more. So here you are adding all these probabilities. What we want is the probability of x is greater than or equal to 7. But this is adding all the probabilities for x equals 7 plus x equal 8 up to x equal 12. Now this adding probability is what we mean by cumulative distribution. Cumulative distribution, in this case, is actually the sum of probabilities. In this example, we are calculating the probability x is at least 7, meaning x is greater than or equal to 7. So that's why we have to add all those probabilities. This is طبعا a lot of calculations. You have to calculate each of these probabilities and add them all together. That gives you 0.9562. there is a high probability. Actually, this is very close to 1. very close enough to 1, and there's a high probability that there will be 7 or more cars that have occupants that are wearing seat belts. There is a table in your book, or at least one of the prints of the book that we use have a table for cumulative distributions, for the binomial distribution. طبعا this will save you from doing every calculations. You can probably use a table to find the cumulative probability. The next and final distribution we'll consider in this chapter is the hypergeometric distribution. Now this distribution is also a discrete distribution. It has some of the features that the binomial distribution has, but it is a different distribution. There is an important difference, which we will see. The hypergeometric distribution comes up when you are sampling from a relatively small population without replacement. Now, we discussed what that means. When you are taking a sample, if you do it with the replacement, that every time you pick something from the population, you return that if it's a population of people, مثلا, in this case, the example we did before was cars. But if you sample with the replacement, that means every time you pick something from the population, you put it back before you pick the next item. But sampling without replacement, that means you pick the items one at a time without putting them back. So that's an important difference. Then in this case, the probability will change. Every time you pick an item from the population, the probability will change. that now will give you the hypergeometric distribution. Here is a list of the properties or the conditions for a hypergeometric experiment. An outcome on each trial of an experiment is classified into one of two mutually exclusive categories, either a success or a failure. This is the same condition for the binomial experiment. Second is that the random variable is the number of successes in a fixed number of trials. This is also common with the binomial distribution. But here is number 3 is the main difference, that the trials are not independent. And that is because you're sampling without replacement. But the trials are not independent. The probability will change every time you pick an item from the population. Now, for the final condition, we assume that we sample from a finite population without replacement, and that small n divided by capital N is greater than 0.05. Here, by the way, small n is the size of the sample, capital N is the size of the population. That you assume in small n divided by capital N is greater than 0.05. When you are solving problems that deals with the binomial, this condition is normally satisfied. You don't need to worry about it. Because that's the main difference, is that you are sampling without replacement. The trials are not independent. The probability of success changes for each trial. Let's look at an example of the geometric distribution. We also have a formula to calculate probabilities for the hypergeometric distribution. P of x, I'm going to read the formula and then explain what each symbol means and then come back to it again. Here the probability of x is S choose x. Here S actually is the number of successes in the population. Again, remember there is an outcome that's considered to be success. Then here S is the number of successes in the population. If I take S choose x, we're calculating the probability for x. If S choose x, this is multiplied by n minus s. And remember now, capital N is the size of the population. Subtract s, which is the number of successes in the population. Choose small n minus x. Small n is the size of the sample, and x is the value that you are calculating the probability for. This is divided by capital N, choose small n. The size of the population, choose the size of the sample. Let me read those symbols again and then come back to the formula, because we will use it to calculate some probabilities. Again, capital N is the size of the population. Capital S, there's only actually S here, is the number of successes in the population. X is the number of successes in the sample. That's what we're calculating the probability for. It could be 0, 1, 2, up to the size of the sample. Small n is the size of the sample, and C is the symbol for a combination, which we already know how to do this. Again, let me read the formula one more time and then use it to calculate probabilities. For the probability of x is S choose x, the number of successes in the population, choose x, that's the number of successes in the sample, multiplied by n minus s, choose small n minus x. You are multiplying those two numbers. This is divided by capital N, the size of the population, choose small n, which is the size of the sample. Here is an example. Playtime Toys Incorporated, this is a company, employs 50 people in the assembly department. Then N, big N, the size of the population, is 50. 40 of these employees belong to a union, يعني they are union members. Here belonging to a union is considered to be success. You have 40 successes in the population, يعني capital N, the size of the population is 50. You have 40 successes, 40 successes, meaning 40 people that belong to the union, which means طبعا 10 do not belong. يعني in the population of 50, 40 successes, يعني 40 belongs to a union, 10 do not belong to the union. Now the sample we take will be 5 employees are selected at random to form a committee. Your sample equal to, يعني small n is equal to 5. We want to know what is the probability that 4 out of the 5 people in the sample belong to a union. Here again it's important that you يعني record those different values because you will use them as substitution. The first number you need is capital N, which is the size of the population, which is in this case is 50. Then S, the number of successes in the population, is 40. Then I have 40 people who are union members. My sample size is 5, for small n is 5. We're interested in the probability that 4 of the 5 belongs to a union. يعني x here is equal to 4. طبعا applying the formula, you want P of 4, x is equal to 4. Take S, the number of successes, which is 40, choose 4, that's the value for x, multiplied by 50, which is capital N, minus S, يعني 50 minus 40, choose 5 minus 4. طبعا 5 is small n, the size of the sample, and 4 is the size, يعني the number of successes, the value for x. Divided by capital N, choose small n, يعني 50, choose 5. Again, one more time, you take S, choose 4. يعني S here is the number of successes, 40, choose 4, times 50 minus 40, choose 5 minus 4, divided by 50, choose 5. طبعا 40 choose 4, you need a calculator, you should get 91,390. Multiplied, this number here now is just 10, choose 1, which is 10. The denominator is 50, choose 5, this is 2,118,760. The result of this calculation is 0.431. يعني the probability in 4 out of the 5 people in the sample belong to the union is 0.431. In the next slide, I think the remaining calculations, يعني the probability for the other values for x, are calculated for us. This is the last slide. This is now the distribution for the hypergeometric probability distribution we just looked at. طبعا the union members in a sample can be either 0, 1, 2, 3, 4, 5. We calculated the probability for x equal 4, and there are 4 out of the 5 people in the sample belong to a union. The probability was 0.431. The probability for the other values of x are already listed. It seems that the probability that none of the people in the sample belongs to a union is close to 0, or you can consider it to be 0. And then طبعا the one we calculated was the highest probability, the probability that 4 out of the 5 belong to the union is equal to 0.431. And طبعا this is not a surprising يعني result, لأن out of the population of 50, 40 of them belong to the union. So in a sample of 5, the probability that 4 of those people belong to a union is 0.431, which is the highest probability compared to the other probabilities. طبعا the final probability in all of them belong to the union, يعني x equal 5 is 0.311, and طبعا the sum of all those probabilities is equal to 1. This is the end of this tutorial. طبعا يعني there are more examples about the يعني discrete distributions and how to calculate the mean and variance and standard deviation. There is also more examples in your book about the binomial and hypergeometric probability distributions. And طبعا in both cases you have formulas to calculate probabilities, but you need to recognize the problem as either binomial or hypergeometric in order to use these formulas.